Okay. So, these three chapters that we're going to discuss, okay, they basically are what you call modern physics, okay? And modern physics is actually with respect to Newtonian physics. So the Newtonian, the mechanics that was developed by Newton and later on by other people, okay, was put in question based on some experiments, okay? The first experiment that we discussed was about trying to understand what we call black body radiation. Black body radiation is the radiation of the body in the absence of any external light. So if you take anybody, you put a camera, okay, and you close all the windows, there's zero light coming in, a priori you should not see anything. But if your camera is in the right wavelength, then you discover that you're able to see. And this light coming from the body is caused by these electrons, the collision of the electrons, of the atoms between themselves. And thus you have some electrons which are excited, some electrons which are disexcited. And what you see is the result of this excitation and giving you this light, okay? And so what people try to do is that they try to explain this using Newtonian mechanics, and they failed, and this led to what we call the ultraviolet catastrophe. In few words, when the temperature of the body changes, you have the light intensity which changes. So the higher temperature, the higher intensity, and the shorter is the wavelength following Wien's law. Okay. And then, in order to explain this process, we had to abandon this idea of continuity. This is a very important revolution in our thinking, because you take a look at everything around you, and everything is more or less continuous. Okay, but now these results they force the physicists to really, let's say, overcome their first thoughts, okay, and to come up with something a little bit deeper, actually, which require a discrete set of energies and not a continuous energy, okay? This was done the first one was done by Max Planck, okay? He was able to describe the black body radiation by assuming that the energy is not radiated continuously, but in a discrete set of wavelength or a discrete set of frequencies. So then came the photoelectric effect that we discussed, where actually it was the first time that we put together electricity and magnetism and photoelectric effect. So we have light on one hand, okay, and electric setup on the other. Like here you can see you have a battery, you have electrodes, okay, basically it's like a capacitor, okay, and you have light on top of that. And so the main findings is that first, what is the stopping potential? The stopping potential is the potential above which you start to record the current. This is one. Two, the more the light intensity you have, so the more you have photons, the more you have current. Three, the kinetic energy, okay, which is 1/2 mv squared, does not depend on the number of photons, but depend on the frequency, hf minus phi, okay, where hf is the energy of one photon, okay, and phi is the work function of the metal, which really is the energy that the electron must take in order to get out of the metal. This is what's described here. So omega 0 or phi, depending on the books, is called the work function. HF is the energy of one photon, and Ke max is the maximum energy of one electron. Okay, so I hope that you get this right. Okay, and this is the summary. Of course, when HF equal to phi, so basically the energy of the photon is equal to the work function, then the electron will have a kinetic energy equal to 0. okay? And so it's unable to escape, but it is still, it is able to get out of the metal, okay? Okay, so one of the major consequences of this experiment and this explanation, okay, is the fact that now the electron, the light is no longer going a straight line. Other modification is going into wave, and the third modification is it is a particle going into. But this particle has a specific properties, such as its mass is equal to 0 and it is not charged. Okay. Now you can say, oh well, how come the photon has a mass equal to 0? Well, if you look at the electron and the proton, you can clearly see you have been taught that the mass of the proton is 2,000 times that of the electron. Okay, so you can see that you have particles which have different masses, and why not mass equal to 0? Okay, this is one. Two, the photon has a charge equal to 0, and we know we have particles inside the nucleus, which are the proton and neutrons. The neutrons, even though they have the same mass as the protons, but they have a charge equal to 0. Consequently, you can have three different charges: positive, negative, and 0. And the photon, the main property of the photon is to have mass equal to 0 and a charge equal to 0. Now we're going to continue our third experiment, which is called the Compton effect. So in the photoelectric effect, we have the photon hitting the electron and changing its property. Here we're going to use an X-ray. Okay, give me a second. No. Okay, wait. So we probably will see that in one section. So in the atom, you guys have learned that you have the nucleus and the electrons, which are zipping around. Okay, all right. Now the nucleus is formed out of protons and neutrons. Okay, what I'm trying to say is that these are what we're going to call elementary particles. Okay, but we can add another elementary particles to the proton and neutron and electron. Now we're going to add a photon. So a photon is basically like a fourth elementary charge. Okay, an electron is charged negatively and have a very small mass. The proton is charged positively and have relatively large mass. A neutron has roughly the same mass as the proton, but charge equal to 0. And the photon has a mass equal to 0 and a charge equal to 0. Okay, I hope this is clear. So now instead of launching light and get the electron out, what we're going to do, what Mr. Compton did, okay, is that he directed a beam of X-rays towards a block of graphite, okay? And he found that the scattered X-rays are slightly longer wavelength than the X-rays, initial X-rays. And this means that they also had less energy, and this less energy went into the electron. So what is actually happening? Okay, so here's what we have. Okay, what we have. So we have an X-ray. Okay, which has a frequency of 0 or a wavelength lambda 0. Okay, and now it's going to interact with the graphite, which is carbon basically. Okay, with the graphite, and so it's going to interact with it. All right. And so the idea is that I'm going to launch my X-ray, okay? And on the back, I'm going to record the frequency of the X-ray which are coming after the interaction between the emission X-ray and the block of graphite, okay? And what Compton noted, he noted that the frequency or the wavelength of the X-ray after interacting with the graphite is different from the one that is incident. Okay, and he had a empirical description where the formula was equal to some constant h divided by MEC, where Me is the mass of the electron, 1 minus cosine theta. Okay, So if now, so what's the idea is that, okay, now we are more and more thinking of a photon as a particle, as as like a sphere, okay? So a bit like an electron, but with a mass equal to 0 and charge equal to 0. Okay, so we have now a photon coming in. It hits it interacts with a electron. Then the electron goes. It's called the recoiling electron. It has some energy now, and this one lost some energy, and then it goes into some another wavelength f prime lambda prime. So this is the essence of the quantum scattering. That is, it's the change in the frequency or the wavelength of the X-ray. Okay. After interacting with the electrons of the graphite block or any other, basically, or any other material. That's the what you can see here on the right hand side. This is the figure which is actually taken from his article, from the article of quantum. Okay, and what you see is that if you use classical mechanics, we have this this prediction here, which is the dashed line. And if you use quantum mechanics, we have this solid line. And you can clearly see that this solid line fits in extremely well with the experimental data. Now, the quantity h over MEC is called the quantum wavelength, and it's equal to 0.00243 nanometer. Okay, so it's a very small amount. So please recall that the quantum shift depends on the scattering angle and not on the wavelength. So basically, this is shown here. You see, this is shift. The shift is the final wavelength minus the initial wavelength. Okay, so this difference only depends on theta. H over MEC is a constant. Okay, H is a Planck's constant. We saw it with Planck. E is equal to HF. ME is mass of the electron, and C is the speed of light. Okay. All right. So overall, okay, what we can say, considering these three experiments, is that light has a dual property. Okay, it's like you have a coin with double face. Okay, one face is wave, and the other face is a particle. And the nice and really the interesting part is that light will act like a particle if it's interacting with a particle, and it will act like a wave if it's interacting with a wave. Okay, so it's not on its own. Okay, it needs an environment. It really depends on the environment in which it's going to behave. Okay, so wave-particle duality is the concept that all matter exhibits wave-like and particle-like properties. We will come back to that a bit later. So what we said here, the duality addresses the inadequacy of classical concepts like particles and waves to fully describe the behavior of the object. Okay, so this is what I would like you to remember, is that light has a dual nature. It's like a dual nature or maybe dual property, and it will act like a wave if it's interacting with light, and it will act like a particle if it's interacting with particles. Okay. All right. Now we come to our friend Mr. De Broglie. Okay. All right. So we said we have been like there was some like a small trip. Okay, between you have Max Planck, Albert Einstein, and then quantum, and then we have De Broglie. De Broglie had the following idea. He said that, okay, you know what? Okay, photons have this dual nature between particle and wave. Great, that's good. But you know, photon, as I was just explaining, is just a particle. And a photon is like the electron. Okay, so if the photon has a dual property between as a wave and as a particle, then all forms of matter, all elementary particles will have the same property, and that is they will behave at the same time as a wave and a particle. And so what he did is that he said, okay, if I take the momentum, I think that you guys all know the momentum. P is equal to mv. Well, P is equal to mv, I can write it as simple as h over lambda, okay? Where or lambda equal to h divided by mv. So what does this mean? This means that if I have a particle with mass m, I can find the equivalent wavelength. It equivalent, so basically mv is the momentum in the classical world, h over lambda, or in the particle world, excuse me, the particle world, h over lambda is the momentum in the wave world. But of course they are the same, it's the same particle, okay? So from this equation here, you have a equivalence between lambda and m, and mv, of course, sorry, and mv, via this constant h, okay? We will come back. So for light, okay, light travel at the speed of light, okay? So v is equal to c, all right? You could say that m is equal to 0. M equal to 0, but I can use a different equation that is p is equal to e over c, okay? Leading to E is equal to HF. Let me just so what we are trying to say here, and this is very important, okay? That is light, that is, if I have a wave, okay, with a wavelength lambda, it has a momentum. This momentum is equal to h over lambda, okay? So please remember it like this. Okay, if I have a wave with a wavelength lambda, then this wave will have a momentum p equal to h over lambda. Now, if I have a particle with a mass m going at some velocity v, then this particle will have a momentum p is equal to m multiplied by v. Now, in the general case where these two particles, these elementary particles have at the same time a particle nature and a wave nature, then P equal mv equal to h divided by lambda. Now, but nevertheless, please remember that the definition of P, which is equal to mv, okay, is not only related to mass. So I can have only a wave h divided by lambda. And this is the case for light. Light, it has a mass equal to 0, but it has a momentum, and this momentum is equal to h divided by lambda. Okay. Now you can probably, I don't know if you guys, P is equal to E divided by C. You can ask, okay, where does this come from? Okay, let me give you an idea. Wait a second. Where this could come from? I just need to. Okay. You guys all know that the energy, okay, the kinetic energy, E is equal to 1/2 mv squared. I think you all agree with it. Okay. Let us for the second skip the 1/2. We don't care. Is equal to mv squared. Okay. Now, if we talk about light, the velocity v, if you want to relate the momentum to the potential, then I can say that by P, which is equal to mv, is equal to E divided by V, right? So in the case of light, okay, I can skip this P equal to mv, and I can say that here, that P is equal to E divided by V, and this is in general. If I'm now talking about light, so for photons, okay, we have P is equal to E divided by C. Sorry. And you can tell me why am I doing all these calculations? And the reason why I'm doing this calculation is that I'm going to try to convince you that mass actually is not something which is essential, or it is a necessary quantity to have a momentum and to have energy. I can have energy E equal to HF, and I can have a momentum E is equal to HF divided by C. That is the main point that I'm trying to make. Okay. So, let me see. Okay. So the de Broglie concept generalized Einstein theory for photons. So now I have all the electrons, so I can take electrons, and I can, and the idea is to prove that these electrons can behave like a particle. We know that. We know electrons behave like particles. You know, we have a lot of like current is one example. Resistivity is one example. Okay, but now we want to show that it actually can behave like light. And this is the experiment that I'm showing here. Okay, what you see these lights. This is the interference. Remember, we saw interference with light with two font. Okay, and this is exactly the same experiment, but now we are using electrons instead of using light, and you can see that you have an interference pattern. Okay, so this idea that not only the photons have a dual nature, particle and wave, but all other elementary particles is confirmed in an experiment, and the relationship between the two is P equal to mv, which is equal to h divided. Okay, my final say here, of course, you guys look at this equation and then you go, what is this? Well, of course, this is not included in the book, in your book. I put it because I think it's a little bit, it's pretty well. Okay? And to show you that actually what physicists did, and mainly Erwin Schrödinger in 1926, is that, okay, now we have the photon of Einstein, we have the energy discreteness of Max Planck, we have the quantum effect, we have de Broglie, okay, but you know, we still don't have the equation like Newton. Okay, let me remind you, what is Newton? Newton is the main mother equation for all mechanics. Everything concerning classical mechanics is started with Newton. Everything. Okay? Now, for quantum mechanics, okay, we still need the same equation, the same formula. Okay? Exactly like sum of the forces equal mass multiplied by acceleration. This is the equivalent of sum of the force equal mass multiplied by acceleration in quantum mechanics. And psi is called the wave function. So, so it's called the wave function. I'm going to skip here. Okay. Yeah. Psi is called the wave function. So, and this is for your own knowledge. So, what does quantum mechanics do? Quantum mechanics is a description, once again, exactly like Newton. Newton is also a description. Okay. Newton invented the concept of a force, and he said that the sum of the force equal mass multiplied by acceleration, and then this has led to this success. Okay. Now, Schrödinger and co. So there's a whole group of scientists. Okay, de Broglie is one of them. Fermi, Einstein, etc. What they did is that they said, okay, if I take, for example, this pen, according to Mr. Newton, he tells me this pen is here and moving at this speed. Okay. So what I'm going to say in quantum mechanics, I'm not going to say that this pen is here. I cannot say this pen is here because it is at very tiny scales, and we'll come back to the issue of errors, okay, later on. But I'm going to say that I'm going to describe this pen is somewhere, okay, is somewhere, and I'm going to describe the highest probability it is here. Okay, so we have two steps. Step one is it is you have a wave psi equal to k cosinus kx minus omega t. That's the function. Okay, that's the wave function. It's a wave. Okay, so it's cosine or sine. Okay, and on top of this, so but the cosine is everywhere. Okay, it's going everywhere. You don't know where it is. If I take psi is equal to a cosine kx minus omega t, then it's everywhere. Okay. Then I'm going to couple this with a probability, and the probability of finding an object is described by the amplitude square, okay, by the amplitude square of psi. So the value of psi square at some location at a given time is proportional to the probability of finding the particle at that location at that time. So Schrödinger equation plays a role of macroscopic particles analogous to Newton's second law in classical mechanics for macroscopic particles. So the goal of this section here, this 3 slides, is really to introduce you to what most probably you and probably your friends or your colleagues or your neighbors or your sisters, okay, whether they will tell you about quantum mechanics. What is quantum mechanics? Quantum mechanics describes the atomic world. So all these laws will apply only at the atomic scale. Once you go at macroscopic scale, you go back to our friend Mr. Newton. Okay. So this description is based on 2 things. 1, a wave description, and 2, a probability description. So I can no longer say that my pen is here and moving at some velocity v. I can say that my pen maybe it has a higher probability, it has a high probability that it is here and it's moving at some velocity v in this direction. This is the essence of quantum mechanics in few words. Finally, we're going to end this chapter by going into this uncertainty principle of Heisenberg. So as I said, you have our friend Schrödinger, Einstein, Heisenberg, and he did something really very important. Okay. So when measurements are made, the experimentalists, they always face with experimental error. Okay. So now you can assume that that if I am an experimentalist, okay, I'm looking for my electron, okay, and I'm looking for my electron, and the more I'm able to make a precise measurement, the more I'm able to tell where my electron is, right? It seems logical. However, but since now I can no longer tell that my electron is here, I can only tell it has a probability to be here. Consequently, in this description, there is an inherent lack of information because I cannot tell my electron is here. I can tell it has a higher probability to be here. For example, it has 99% of the probability to be here, but I still lack 1%. Okay, this 1% or this lack of information is described in what we call the Heisenberg uncertainty principle. Okay, so this uncertainty is not caused by the measurement, but it's caused by the description, the quantum physics description. So it's much more fundamental. Okay, and consequently, if a measurement of a position of a particle is made with precision delta x, with a simultaneous at the same time measurement of the linear momentum mv is made with delta px, so this is the error, then the product of the two can never be smaller than h divided by 4. This is the direct consequence of a probabilistic description of atoms by quantum physics, because the probabilistic description inherently contains a lack of information because it's a probability. We don't know. Yeah, maybe it's here. Quite probable it's here, but we don't know really if it's here. Okay, and this is described here mathematically. Delta x, which is the error around the position, multiplied by delta p, which is the error about the momentum, must be greater or higher than h divided by 4 pi. Now I can turn my p into energy and my x into time, and I have a different form of the Heisenberg uncertainty principle, that is delta E multiplied by delta T must be greater than h divided by 4 pi. Let me just see what I have. Now, okay, you have to understand, I hope that you guys understand, okay, is that quantum mechanics is a very challenging, bring to us challenges. One of the challenges is this discreteness of energy. How can energy be discrete? I mean, okay, next chapter will be dedicated to that, okay? But also, if you remember, I told you this duality between the photons, and then later on by de Broglie between any particle. This duality between particles and waves, right? And what I said is that a photon will act like a wave if it's interacting with a wave, and will act like a particle if it interacts with a particle. So what does this mean? It means that the photon does not live in its own world independently of the outside world. Okay? In other words, it really depends on the outside world. It's not something that it's not a pen independently of the background. No, it can be a pen or it can be a phone, whether I have a pen next to it or a phone next to it. Okay, so this is also described. This is another way actually of describing what we call the uncertainty principle, and that is usually always never a particle is observed in its ground state. You have to excite it. You, as observer, play a very important role in the way the particle is going to respond to you. If I am a wave, then the photon will act like a wave. If I'm a particle, the photon will act like a particle. So in this case here, the observer is no longer someone or something which is quite independent from what he's observing. And this is a challenge. This is something that raises a lot of questions, and it has a lot of philosophical consequences. Okay. Okay. I hope that you guys understood. I'm gonna have. Okay, I'm gonna leave it. I'm done with this chapter. I really would like to hear your questions. I hope you have questions. We still have 3 minutes. If we cut, then I'll restart again. Okay. Questions, guys?
I have a question about the Schrödinger, I think, equation.
Schrödinger.
Yeah. How could we use it?
No. This is no, Halil. This is not required. Okay, this is not required at all. At all, it's not required. Okay. I put it just as I put the picture of Mr. Schrödinger. Okay, just to give you an idea.
So we just have to learn about the concept, but not apply it.
Exactly. Not at all. Not at all.
Okay.
You need to learn two things: that psi is a wave function, so it's a wave like a cosine kx minus omega t. Okay, and two is that the amplitude of psi square is proportional to the probability of finding a particle at a given location at a given time. These are the two things that you are required for.
Okay, thank you.
Okay, but definitely not the equation itself. أكيد لا.
Okay.
Okay. Other questions? It's going to rain.